Okay, in this video I'm going to show you how to determine g for a planet. And of course we know that g is the acceleration of gravity, and on Earth g is equal to 9.8 meters per second squared. But in general, if you go to other planets, g is going to have a different value. So what I'm going to do in this video is kind of show you how we can use the universal law of gravitation to come up with a neat way to calculate g that's pretty simple. So I'm going to start off by drawing a situation here. This is going to be for a uniform gravitational field. And what I mean by that is that if this is the ground here, that I'm not going to talk about going to extreme heights above the ground. We're just going to stay close to the surface of the Earth. Okay. So let's say that I have a ball here that's pretty close to the ground, and let's say that that ball has a mass of 2 kgs. Okay. The gravitational acceleration of the ball can be thought of as the ratio of the ball's weight to its mass. Okay, so this, I hope you recognize this. This is just the formula that weight is equal to mass times gravity, and it's rearranged. And truly, we would define the gravitational acceleration this way. If you can measure how much something weighs and divide by its mass, that's the acceleration. So this object, let's say that it weighs 20 newtons. You divide that by 2 kgs, and you get an acceleration of 10 meters per second squared. You know, you could try that. That could be an experiment, and you would determine g that way. Okay. Now, if you move that object up a little bit, like you go to the 2nd floor of a building, or the 3rd floor, or the 50th floor for that matter, you take the same object, and again, you weigh it in that location further up, and I'm pretty much going to guarantee that you're still going to weigh 20 newtons. You divide that by 2 kgs, you still get 10 meters per second squared. And so the idea would be that the gravitational field really does not change very much in those two locations. I could represent it with a vector here and here. And those two vectors for the acceleration would in fact be equal. Okay? And so that's important because we rely on that for a lot of the problem solving that we did, especially with projectiles, is that we assumed that things didn't really go very far away from the Earth. Okay, now let's look at the case where you have larger changes in position for an object. So now we're going to look at a case for a changing gravitational field. And the question would be, well, how does that happen? And now what you have to do is you have to kind of expand your thinking, and you have to think about big changes. So I'm going to draw kind of the Earth here. It's supposed to be the Earth. And then I'm going to put my 2 kilogram ball kind of at like 1 Earth radius. Meaning it's going to be on the surface of the Earth. And so if I do my experiment here, and I say, well, what's g at that position, I would find that g is equal to the weight of the ball divided by the mass of the ball. Again, it's going to be 20 over 2, which is 10 meters per second squared, just as you'd expect. Okay. But now what would happen if you took that ball and then you brought it in a rocket and you lifted it up to a position that's now at 2 Earth radiuses. Okay, so that's really a big distance, right? The radius of the Earth is pretty big. So you're not talking about going to the top of a tall building. You're talking about being out in outer space. Now, if you do that, what's going to happen is that the gravitational force on the ball is definitely going to get weaker. And hopefully now you know how much it's going to get weaker by, right? So if you take two objects, if you've got the Earth here and a ball here, and they're separated by a distance r, that gives you a certain force. If you double the distance, the force should actually go down. And it's not going to go down by half, but it's going to go down by 1/4. So my G value in this location is now going to be equal to 1/4 of that weight, divided by the mass of the ball. And I guess if you want to put numbers in, you could say 1/4 times 20 is 5 newtons, divided by 2 kgs, and that's 2.5 meters per second squared. Okay. Now notice 2.5 meters per second squared is actually 1/4 of 10. So what we've done is we've doubled the radius and we've decreased the force by 1/4. We've also decreased the acceleration that much. So if my G vector looked like this on Earth, when I get up here, it's going to be short. I'm going to be 1/4 as much. Now, if you're following the logic here, you could now go to, say, 3 Earth radiuses, and we're measuring from the center of the Earth to that point. And I hope that you're with me on this, that the force is now going to be 1/9. So the weight is 1/9 of its original value, divided by the mass of the ball, which does not change. And that's going to give me 1/9 times 20, which was my original force, divided by 2. And that's 1/9 times 10, and I don't know what the decimal is for that, but 10/9. And the point would be is now we're at 10/9 meters per second squared, or 1/9 of the original acceleration of gravity. So the point is that the value of G changes as you get farther from the center of a planet. And it follows an inverse square pattern. Okay? As you can see from these numbers, you're going from 10 to 2.5 to 1 point something, right? It's getting small, and it's getting small fast. So that's something that's worth noting. If you're an astronaut or if you're NASA, you're going to need to know that to understand how your rockets are going to be affected. Now, mathematically, how do you calculate G if you don't do it this way? It's pretty straightforward. Weight of an object is equal to mass times gravity. Okay, this is the mass of the object. I'll put an O there to represent the mass of the object. Now, gravitational field is equal to weight divided by mass of the object, like we did earlier. But now what I'm going to do is, instead of writing weight, I'm going to substitute the law of universal gravitation. And so I'm going to write G times the mass of the object times the mass of the Earth divided by r squared, where r might be the radius of the Earth, all over the mass of the object. Okay, that's a lot of symbols and things, but if you're looking at the symbols, you see that you're going to be dividing out this mass of the object. And so the object itself doesn't affect G. G is really just related to the mass of the Earth and the radius of the Earth. So what we have here is a formula for G, which goes like this. Right? That simplifies. And that gives you the value at sea level for the gravitational acceleration. Okay. You can try this, you can calculate it. It's actually a great thing to do right now. Use the value of G that we wrote down the other day. You've got it in your notes. The mass of the Earth is about 6 times 10 to the 24th kilograms. The radius of the Earth, it's about 6.38 times 10 to the 6th meters. And you guys already know that g is equal to 6.67 times 10 to the negative 11th meters. I'm sorry. The units are newtons times meters squared over kg squared. But if you take a second, go ahead and calculate, multiply these two numbers, and then divide by the square of this, and you're going to get something which is really close to 9.8 or 10 meters per second squared. Okay. So you can do that. That's a good thing to try. If you are not at sea level, then the radius can be different. And so let's say that you're in space or something like that. So now r is any distance from Earth's center. Okay, so if you want to know what g is in any location, you have to basically know the distance from the center. Be careful when you do this. It's not, remember, that distance is actually the distance from here to here, to the object, right? And it is not the distance from the surface. It's not from here to here. It's the distance from the center of the Earth to that point. So just keep that in mind when you do your calculations. Okay? So anyway, I think you've got a nice formula here for figuring out g in a couple of different situations. But anyway, that's where it comes from, the physics behind it.